All right. I'm gonna start looking at a bug just to get things starting. So yesterday I did some changes to the Flashloader, and it seems that didn't work for everyone. So let's have a look at that. So the report is basically that there is a message when you load this, when you run the script, you get something like this. That we get past this step where we load the image into RAM, but then you get this message, which looks like an OpenOCD help message. So it looks like there is an argument that is not being passed properly. So yeah, let's have a look at that. So in Flashloader, what we do is that we have a binary that has a bunch of variables located in various locations that we extract. And then there is a script that loads it. So we set these variables to certain values. And in this case, I changed the way that size is being evaluated in the script. And it would seem that this does not work for everyone. So maybe this is not platform agnostic. So the idea is that this should work on basically any platform. So if you, for example, take the make file, then you should get the number of bytes in the make file. But for some reason, this person did not manage to get any value here. So I don't understand really why. Very strange. Yeah, let's try to figure out why this happens at all. But yeah, good morning. Yeah, hi. So I'm looking at the Flashloader, trying to figure out why this line does not work for everyone. So my idea was, or rather, I'm looking for a way to get the file size, and it should be platform agnostic. And it seems, yeah, here I need two programs, word count and cut, which are very common programs, and I think they should work on Mac as well, I think. But maybe I'm doing something wrong. So I don't know. I could add a failsafe. So if this evaluates to nothing, basically. Then we set it to 1 megabyte. But I don't really like that at all, actually. Yeah. It is actually kind of a hard problem to get the file size. It seems it should be something easy, but actually it's not that easy. At least not if you want to make it platform agnostic. I don't know. So if we just do some Googling, portable. Yeah, so here someone is suggesting word count, which is POSIX. So that should be fine. But stat is a little bit different. Hello, nickname 77. How about just failing? You can use size argument anywhere, right? Yeah, but ideally I want the scripts to like work on their own, so it just works. Because people will be complaining. Did the person check the result of VC command alone? No, it's from the Discord in the emulator room. So I can show you the error message. So I'm just gonna do like this. So this is the error message from flash.sh, and as you can see, we get past this step, loading image into RAM, which is here. And then we get this message, which looks like an error message from, or rather a help message for how to use the command from OpenOCD. So I'm guessing it's this command that is being executed without the size argument. So I'm guessing that size is evaluated to nothingness. It's just an empty string, which would happen if this does not work. So if this returns an error, and if there is just an empty string. But yeah, the idea is to get a number back like this. I don't know, is cut not platform agnostic? I guess if you're on Windows, you might have some issues, but I guess then you would have tons of other issues. I don't know. There might also be like a time zone issue, so even if I ask, we might not get an answer today. So I don't know. I think this should be fine. If anyone is on Mac in the stream, it would be really nice if you could try out this line. Just run this command, wc-c, and then a file name, just to see that you get something back, like so. Yeah. Maybe there are. Yeah, Mac is so. I have a Mac, but not right now, and I don't want to leave the stream because that's gonna be annoying for you. But it would be nice to have like a an SSH to just hop into a Mac machine somewhere. But yeah, maybe we should just leave it as it is and look at this later. I just wanted to look at something while we were sort of waiting for people to join. So I guess this is yeah. Let's look at this later and see why it's happening. Yeah, so we can take a look at a few changes. What has been going on since last time? So when did we stream last time? That was. Here's the profiling stuff. Yeah, here's the scaling. Okay, yeah, so the biggest changes since last stream is probably the Game Boy. So stacksmashing found the root cause for the sound glitches, the bad sound on Game Boy. So that has been fixed now. So that's really, really awesome. So now you can use Game Boy and enjoy fluent sound, no glitches at all. So that's really, really nice. I did some fix up in the rendering after the stream. Yeah, I did some refactoring. So yeah, with the makefiles, maybe that is important to talk about a little bit. So previously you needed a directory called drivers with or you still need that, but you needed to prepare that yourself. But now that is being handled by the makefile itself. So the idea is that you just check out the project and then you can just build. So let's see if I have. Oh, I don't. Yeah, let's just clone. So you just clone the repository, you get the submodules. This might take a while because it's quite a huge one. Yeah, I'm gonna cheat a little bit and just copy it from my home directory. And then we can. Oh. Yeah, so all right, you need to have a ROM as well. Anyway, you just build it like so, and then something. All right, you need Flashloader as well. Yeah. So the idea is that you just clone the repository and then you make, and it will download the SDK automatically. So I think that will be really helpful for people who have trouble with getting started. So this way you don't need to sort of manually click a button in STM32 CubeMX and so on. So hopefully this will make things easier for people. Yeah. Okay. I did some more changes. Mostly a little bit of cleanup, but yeah, I guess this commit will make state saving work again for NES. That was broken for a little while. But yeah, that works now. Yeah, I pumped up the white balance to the warmest setting, but now the white actually looks white on the camera. Let's see here. And also, this demo is using some uninitialized memory in the frame buffer. So previously, I sort of loaded a borked out state save, which yeah, which makes it look really odd. But anyway, this is how it's supposed to look. But yeah, so it looks a little bit better. So that's nice. Okay, so what should we do now then? There is so much to do. There are many things we want to do. So I guess the Flashloader stuff we can just hold off a little bit on that. Do that later when we have an answer on why this doesn't happen. Because I think this is supposed to work on many platforms. So yeah, moving on. Let me just clean up here a little bit. Oh, do I have a change here? No. Okay, my editor thought it was a change. Oh well. Yeah, let's just clean up. So what should we do? So people are asking for supporting multiple ROMs. And in order to do that, we need some sort of GUI, because yeah, it's not gonna work otherwise. So I'm thinking of actually using the Game Boy simulator or emulator as a starting point, because we can iterate on it a little bit faster, because it is small, so we don't need to what's it called again? We don't need to flash the external flash all the time. So if we just have a look here at maybe I should do like this. So these are the sizes of the various memory areas. So as you can see, we have 40K of internal flash free, so that we can use for fonts and stuff like that. There's actually a lot of RAM left. Yeah, we have a lot of budget actually. This is really good. So just to compare, let's check out the NES simulator. So yeah, so we don't use any of that RAM. We only use 40K of the GTC RAM. Here's also like a lot of RAM left. But yeah, I think this might change in the future because of the LUT-based versus 565-based rendering. Then here is almost nothing used. I think this is only for audio. I mean, we have a good place to start at. There's a lot of space. The only thing we don't have is internal flash memory. Here we have 70 kilobytes free, which is actually a lot, but the bulk of the NES simulator or emulator is, I think, over 100 kilobytes. So, yeah. Actually, now that I think about it, maybe we can relocate it to this area. I'm gonna try that. Because if we can fit the whole emulator on the internal flash, it will make life a lot easier. Just gonna try to fix my window manager a little bit. Yeah, here we go. Okay, so this is better. i3 is a little bit interesting. Okay. Yeah. So I'm just gonna try to do some changes to the linker file, I guess. I'm gonna use it as a reference. So we want to use the AHB RAM more, because right now we're only using it for audio, literally only audio. So I'm gonna move this down here. So let's see if it fits. Actually, no, this is wrong. I'm gonna move this part. No, that's not good. This is initialized data. That's not good. Just gonna verify something. So let's build. Yep. Okay, this code is being used. Let's just put the data in the normal place. And then let's relocate this. All right. I'm actually not thinking straight. No, let's not do this. I was not thinking. So that all of this is, of course, initialized data, which needs a source, which is the Flash, of course. Yeah, I was just hoping to scratch out some extra space, but yeah, we cannot change. We cannot change this. I mean, the whole issue is that Flash, like either text or data, is initialized text and data, which needs a source. So we need to have it on Flash, either internal or external Flash. It's not about RAM at all. I was just being slow. Okay, so we cannot do that. So let's continue then. We need some sort of UI. So let's have a look at the original code that I have over here. And then let's look at the GUI. So we had a look at this a few days ago, but I can't seem to remember how it was being set up. So I think we have to go through the code again. Oh, here's actually a GUI file. Okay, so the way the code is set up is we have this GUI file, and GUI redraw is sort of the rendering method, which is being called from various places. So this seems to be sort of the main loop, the outer main loop. Okay. So I guess we can try to integrate this outer main.c and GUI somehow. Not really sure why, but I haven't really looked at this at all before. So I wonder, do I have those files here? I do. So maybe we can just build them. So I split up the makefile into a common makefile and then the Game Boy and NES specific files to make it easier to reuse. And eventually we can maybe merge them. Okay, so I'm gonna need to change this a little bit. Okay, and as expected, we have some issues. Maybe it will be easier if I build from here, actually. Because then I can jump to files like this. Okay, so first of all, I think we need to rip out the whole sort of OS stuff, like file and directories, because we don't have that at all. And then some PNG library. I need to build that as well. So let's do that. I guess that needs to be ported as well. So maybe we can start with that. So let's get that to build. miniz.h, okay, where is that? miniz.h. So I guess we need this as a include. Where do we have that? C includes, okay. Okay, that builds now. That was fast. So let's add the GUI, see if it builds. LUPNG. Wow, okay, so now the GUI code actually builds, but we don't use it. So let's just call the GUI redraw from the main function, just to sort of have something. So I'm just gonna do like this. It's a really hacky way to sort of hook into the main loop and just keep drawing the GUI. And of course it doesn't link, which is expected because we have a bunch of functions that we need to implement. Okay, so where does this come from? Okay, it comes from the overlay function. So let's build that. That will probably also come with a bunch of dependencies. So I guess I'm just gonna try to build each dependency until it builds. So let's see this. Multiple definitions. Okay. So right. So I guess maybe we should copy it instead, because we might need to do some changes. I'm gonna do like that. Okay, so the way this code is written, it's it writes straight onto a display buffer. Oh, we have a spammer. Yeah. 1 second. I forgot to open the mod view. There we go. Okay. Yeah. Let's get back here. So yeah. So just going back a little bit in time. So when I did the port in the beginning, I basically just removed everything that was difficult. So all of these sort of integration files are either just stubs or really bare minimum implementations. But now, since we are improving stuff, yeah, we need to implement stuff. So let's look at how this is actually being implemented. So I guess that is this file. Yeah. So it writes pixels onto the frame buffer. That is what it does. And I'm not really sure about the pixel formats, but we can figure that out. Yeah. So I guess we go. No. Here. So we have to implement this function, but our will look different. So we don't need to do any of this, anything like this. No. And then right. So we actually use double buffering now. Oh, I need to fix my config. Just a second. Oh, I'm stupid. There we go. Yeah, that should be better. Okay. Yeah, so here we have a variable active frame buffer, and it is in main NES. And in Game Boy, how do we do it? There. We do the same. So I'm actually gonna move this a little bit to the LCD file. Do like that. And then in the H file, I'm gonna do it. Gonna expose it like so. That way we can access it from all over the place. And just have to remove it. like so. And then just to make sure that I haven't messed anything up, I'm just gonna undo a few changes here and build. So, okay, something broke. Oh, yeah, of course. The LCD code is, of course. Okay, let's build again. No. All right, because I had made this change here. So I just want to verify that everything is still working. Yeah, and the reason why this demo looks a little bit odd is because it is when you boot up. Yeah, here we go. Looks better. Okay, so that works, and I'm just gonna try the NES emulator as well. Just gonna, no, not that. There we go. So just a sanity check, and yeah, as you can see, something is borked. So it seems to be building some extra file. Overlay, okay. Oh, right. I want to stash this file away. Okay, here we go. Which means that the change might work. Just double checking. Takes a little bit longer to flash because it's larger. Okay, this could just be a glitch. Okay, this doesn't look good. Did I mess something up? Probably. Okay, so I broke something. Is it the LCD code that's broken? I just exposed this, put it in a global place and exposed it. And then here's no change. And here is no change. What about the main file then? I just removed that. This should work. That is a little bit strange. And here is basically no change. It's just adding some include files. That's very strange. Okay. No, maybe something is broken. Yeah, it would seem that I have broken something. I'm just gonna try with a different ROM. No. Okay, I have broken something. Crap. Because I was testing this just last night. Okay, so it seems that Ice Climber works, but larger ROMs don't. So I guess we need to fix that. Like an emergency patch. So let's do that then. I guess that's important because not being able to play larger ROMs is no fun. So yeah, let's do some bug fixing instead. So yeah, I've done a tons of changes, of course, all the time. So let's debug it. So I made some changes to the make file so you can start OpenOCD by just typing make like this. It makes it it makes life a little bit easier when you're coding. And then you can just attach with GDB like so. So actually here it looks like everything is working, but it's not. So I don't understand this. Could it be save state related? Let's try restarting it with the button held down. No. Okay. This is very annoying. So something is broken, and I'm not sure what. I guess we have to do a binary search then. Crap. So let's go back a little bit. Right, the ROM cache might be suspect. Okay, so let's disable that and see if it works better. No, still broken. Okay, crap. Well, let's go back in time. Let's go there. What? That's also broken? Oh, I'm starting to see a... Okay, maybe it's the Flashloader stuff. So let's revert this and set it to what it was before. Like so. Yeah. Let's just try it again. Good morning, Nate. So what I'm doing right now is that I found that larger ROMs don't seem to be working on the NES emulator for some reason. I'm trying to track down why. Yeah, and there we go. Okay, so let's check out as main again. Bad habits. Yeah. Okay, so it's confirmed. So the change I did here that we actually talked about in the beginning of the stream actually breaks more than it helps. So I'm just gonna revert it. Yeah, let's just revert it. So the idea is to only flash what you want to flash. So the flash loader, it writes to the external flash, and it can only write 1 MB at a time. And the external flash, the original flash, is only 1 MB. So usually it makes sense to do that. But if your program is smaller, you only need to write fewer bytes. So I just wrote some code in the script so it's actually updates that size in the program. So if you look at the actual implementation, we have these configuration variables that are being configured over OpenOCD, and we have this program size, which is how many bytes we want to flash. And it would seem that that doesn't work well. So I'm just gonna revert this. Um, yeah, that would probably be good. It's always fun when you use words like correctly. Okay. So yeah, there we go. And now we should be able to, just gonna do a second double check to make sure that stuff works. Yeah, and there we go again. So okay, cool. Now we can go back to what we were doing, which was the Game Boy, getting a GUI into the Game Boy emulator. Yeah. Okay, cool. And we're back on track. So let's do a git stash pop. This will give back all of our changes. Okay, I'm just gonna halt the Game Boy because it's a little bit distracting. Okay, so where were we? Makefile dot something. Yeah, so we had the PNG and GUI file. Let's just start with that. Yeah, that builds, and this builds. Perfect. Then we had the other files. Yeah, the Odroid display. Yeah, this is not gonna work. So we need to fix this. Odroid display. So actually, I'm gonna reorganize this a little bit. Do we use this anywhere? No. Let's remove this define. Move this up. And just write this a little bit nicer. It's always good to use defines, because then you know you don't have to guess. Cool. And I'm sorry for the camera if it's jumping a little bit, but yeah, my table is not extremely stable. It is what it is. Okay, moving on. Lines per buffer. Oh wait, that is not at all what we're doing. I think I should just not read this code at all, just do it from beginning. So left. Okay, let's try to understand this code first. What does left mean? It's not even used. Okay. Oh, there it is. Okay. So it's just used for a... Aha, it moves the cursor. Okay, okay. So left and top is X and Y for the start position. Okay. So let's do like this instead. Yeah. So what I'm doing now is I'm creating a type called pixel t, which is either 8 or 16 bits wide. The reason for that is so we can reuse the same code here for both LUT8 and 565 mode. It's gonna look funky anyway, but yeah, let's do it. So what are they doing here? This seems odd. I'm trying to understand what they want to do. So if y, let's go to the original code so we don't get confused. So here they are just iterating over the number of lines they want to render. For example, 5 or 10 lines. And then top top will be the starting position in the frame buffer. For example, let's say 2 pixels from the bottom. Okay, so if y plus lines per buffer is larger than height. No, I don't think we need to care about this, because we don't have a buffer like they do. So because we can just write straight into the frame buffer. Yeah, we don't need to do this at all. Let's just do so stride is how many bytes you need to increment with. But actually, maybe we shouldn't do that. We should just work with the units of pixels and not the actual byte size, because that can get confusing. Y. This is the actual y coordinate in the target frame buffer. Yeah, so we start at top and we iterate until top plus height. And we will just increase y with 1 unit, 1 line for each iteration. Yeah, let's do like this instead. Yeah, and then instead of doing anything of this, we just want to do a mem copy, where we copy to the destination row. We copy from the buffer with times size of pixel t. Yeah, this makes sense. So either this is times 1 or times 2. Yeah, this should be it. Yeah, I don't see a problem with this. Okay, so let's go back and re-enable the rendering. And of course we have tons of stuff to do. Right, so we ifed of this. Sorry. So let's just do like this. Undefined reference. But didn't we just implement that? Oh, okay, so there's a second one. Okay, let's implement that. Okay, well, let's just copy that then. Then we need read battery. That's actually something that we should implement at some point. Not right now, but we should. Um, let's just return something. I don't know. Okay. No. Okay. Whoa. It's a, okay. So this is actually a little bit interesting. So okay, we got something on the screen. So just to show you, we got something. I have no clue what it is. So okay, let's continue debugging. So we are getting the current tab, okay, which is, we can actually debug this and try to understand what is going on. Oh, it's crashing. That's why. Why is it crashing? Um, oh, okay. So we want to write 40 columns with stuff from the list. Okay. Uh, so currently it's just a bunch of null bytes. Okay. But we want to write 40 null bytes. That's odd. Uh, okay. So that is on the stack, I guess. No. Okay. Okay, but why does this crash? This looks pretty safe. Because this is actually a static allocation. Mm. Okay, so it's looking for a null byte, or why is it crashing? So for some reason I can't see the argument, I guess. I don't know really why. Um, but I'm assuming it's looking for a null byte. Well, this is annoying. So let's try to understand this whole code. So yeah, GUI read row list. Ah, thanks. You can check our, okay, so I actually had those here. Yeah, this makes sense. We had 40 bytes and we are looking for a null byte. in this pointer. So this pointer actually looks odd. This seems wrong. Where does that come from? Yeah, but thanks, Jan. That's really nice. This is let's just look at the linker file again. So we actually do have 0 pointers that is allowed on this platform. We have this whole ITC RAM region that is that has its origin at the null pointer, so to say. But this looks a little bit odd. That is a little bit too big. No, this can't be right. Yeah, this pointer is a very strange pointer. Something is definitely wrong. Okay, again, maybe this is. I'm gonna redo this. So okay, so we have some sort of global state called GUI, which is retro GUI T. Okay, and there's an int called selected, which selects the active tab, I would assume. So here we have a 0, and then GUI get tab. What does it do? It takes GUI.tabs index. Okay, so we have 32 tabs, and they contain a name, status, some stuff. Okay, and I guess they are initialized to 0. No, actually not. Here's some stuff that does not look like 0. This looks suspicious as hell. So are we having some memory issue again? So let's try to understand where does GUI come from. So GUI is a global variable here. Maybe we need to call some init function. So let's go back to the original code and see if there is some sort of init. Maybe it's called init. Yeah, look at this. There is even. This looks a little bit odd. So they first call redraw and then they init the tab. But yeah, this main loop is kind of interesting. But something I really don't understand is where all of this data comes from, because we don't really initialize it anywhere. Yeah, look at this. It's a 0. Wait, shouldn't this become a null pointer? Oh, that is what's happening. Oh, that is what's happening. Now I get it. So, because GUI.tabCount is 0, this will actually return a null pointer. But null pointers are valid on this platform. Oh, man. So, that is our issue. So I guess we should just read the source code and do stuff correctly. So let's see if they do something. They do something called emulators.init. What does that do? Maybe it initializes some tab. It does add emulator. Yeah. So as you can tell, I've sort of speed run the integration before. I just ripped out the code and did it as fast as possible. But now this whole project is like technical debt in a nutshell. Like all of my old sins, I will have to pay for them. But that's fine. I've learned a lot on the way, and to be honest, the best way forward would probably be to rewrite everything and like do it nice from the start. Because trying to make this nice now, maybe it's too late, to be honest. But yeah, let's do add emulator Game Boy. Let's do that. So where do we do that? I guess, yeah. Yeah, this is gonna be a bit of work. So the way we're doing it now is that we basically call app main, which is sort of the entry point. Can we just declare ITC RAM as first non-zero aligned address close to 0? And adjust size accordingly. Let me try to understand. You mean that you want to move this slightly further up, like so, or like so, and then put some sort of because I was thinking about this as well, to put some sort of protection, like you put some magic values in the beginning, and then you can see if that is being overwritten by stuff. But yeah, it's a good idea. Let's we can do that, but it will not really. It will help, but it's not the magic bullet. Yeah, I don't know how much do we want to waste. How much is OX100? That's 256 bytes. Yeah, I think we can manage with that. So let's do that, and then we can in the startup script or in the main file, in the very beginning here. Yeah, like after this, let's do a mem set to the null pointer. This looks so funky. And just put a bunch of A 256 or X100. Yeah. Let's call it null pointer red zone. So hopefully, if you dereference a pointer like this, well, what I want to do is to initialize the actual first OX100 bytes, but I guess yeah, okay, now I get what you mean. So let's call this null. Let's do it like this and do like so, and does this make sense? We can actually do like maybe it's cleaner to just write it like so. Let's do like this. And then we can do it like that and like so. So let's see if this builds. Yeah, it builds. That's cool. Interesting. And then I should export this. And then here we do like so, right? Yeah, it works. That's good. So let's just double check that. Oh, someone is overwriting memory. Someone is definitely overwriting memory. I'm just gonna break in main, or in app main. And then we can, yeah, look at this. Okay, so we have already seen that we have an issue. So what I did now is that I put a breakpoint in app main, which is after we have initialized this red zone memory. And here you can see the red zone. And here is some other stuff going on. And now we're in the hard fault handler. And if we look at the null pointer, we see that, oh no, it's overwritten. So yeah, we definitely have a memory corruption bug somewhere. Nice. So I'm gonna commit this so we have this isolated, because this was actually really useful. And I wanted to do this earlier as well. Oh yeah, actually, this will look ugly, but I think I need to do it. Mm. Yeah, it looks messy, but watch point. Yeah, so I don't know why, but I'm having huge issues with watch points. But now I actually have a J-link as well, so I can try with that debugger. So just to illustrate, let's just flash again, and then attach the debugger. One reset halt, and then if I do a watch on the null pointer, okay, here we go. And this is actually our, yeah. And what about now? Wow, okay, I cannot explain this, but the today watch points work great, which is awesome. But I was using watch points as late as yesterday evening, and it did not work very well. Maybe I did something wrong. But yeah, thanks for the tip. This is perfect. This is exactly. Oh, this is our issue. So what can we do now? Um, I actually want to commit this first, so that we have that isolated, like so, and then the main file, like so. And let's call this null pointer red zone. Yeah, that should be it. Cool. Now we can continue. So yeah, we don't actually need to think much more about this, because as we found out before, we had this null pointer tab because of the because there are no tabs. The tab count is 0. This will return null. Um, So this will return null. So we have a null pointer already here. So once we do tab name, we are dereferencing a null pointer, and we're starting to write into random memory. So yeah, thanks for the tip. Now we have like a scientific way or methodic way to debug this. So we need to initialize the whole system. So again, app main is called from. Oh, we don't need to guess. We have that in here. So before we do this, we need to initialize the system somehow. So I'm thinking of breaking this up a little bit. So we have, because I want to sort of avoid coding too much in main.c. So they have this setup where it's a directory called retrogo, which is sort of the umbrella framework thing, whatever you want to call it, the menu system and so on, which invokes each emulator. So here is all of the outer main loop and so on. Yeah, let's just take a second and read some code. So it's basically taking a bunch of strings and populating them into a emulator entry. So there's a there's a global, or yeah, some structure. And what does it contain? Strings and okay, but I'm trying to figure out how it finds the entry point to the actual emulator. Like how does it know which emulator to choose? So I guess it's looking for a magic. I don't know. What is header NES? Let's check it out. It's a bunch of null bytes. Is it a picture? This looks like a frame buffer of some sort. Yeah, I'm guessing this is an image. Yeah. And there's a logo as well. Okay. You make a Nintendo game? No. So this is a emulator project that is running on the Nintendo Game & Watch. So this is the Nintendo Game & Watch, and we are running custom software on it. And there is a project called RetroGo, which is an emulator collection that is running on a different hardware. Can you show it? Yeah, just a second. Oh, so just a second. I'm just gonna comment this out. Oh. So here's a Game Boy emulator running on it, and I think we have come quite far now. We have 60 frames per second, smooth graphics, and the audio issues have been sorted out, so we have nice audio on both NES and Game Boy. And yeah, it's hard to see on the camera because it's a little bit crappy, but it is smooth. I only stream in 30 frames per second, but it's running at 60. So yeah, I think it's quite nice. So right now I am sort of implementing or integrating a menu system so that we can change ROMs, which active ROM, and so on. But that thing I see, you made that. No, 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 no. So this is a demo that someone made. I'm not NES or Game Boy coder. I'm just integrating emulators right now. Oh, okay, I get it. The physical hardware. Yeah, definitely. That's a official product. So it's this one. Okay, so going back to this. So yeah, I don't know if I want to do this on the stream or not, but there's like a bunch of plumbing that we need to do, which is perhaps a bit boring. Some maybe we can skip ahead a little bit. So what does add emulator do? Maybe we can steal, or not steal, but reuse this code. Or if we should take these files and put them in a separate directory. Yeah, I think it would make sense to actually take, yeah, take this directory and put it in a subdirectory so we have some separation. Because we probably need to do like a bunch of modifications here, I think. What should we call it? So yeah, here we have the Odroid specific stuff. And then the RetroGo stuff, maybe. Let's call it RetroGo. And so there we have app main. So I'm trying to figure out how did I end up where I ended up before. So where do we do this? All of the Odroid stuff. So okay, I'm trying to figure out in my head how the project structure works. So here we have a main.c file with a function called appmain. But at the same time, we have this GUI file, or main.c here in the RetroGo project. And that's also called appmain. So how is this able to link? I don't understand. Or maybe it's doing some magic where it reboots. I don't know. I'm guessing the emulators you're porting were original for Odroid. Yeah. Do they use an STM32 SOC2? No, they don't. They use an ESP32, which is actually a completely different architecture. It's not even ARM. It's Extensa, which is kind of funny. It's but the nice thing is that the code base is sort of optimized for microcontrollers, and that way we're able to reuse it because it's it's not written for a desktop PC, and it's not expecting you to have like gigabytes of RAM and stuff. Yeah, No, no, true. Or I mean, it depends on what you mean with SoC. In some way, everything is an SoC, but yeah, it's a microcontroller. But this one is pretty beefy. So this is the product brief. Um, so you have 1.4 megabytes of RAM, which is a lot for a microcontroller. You have tons of peripherals, and it's made for sort of GUI stuff. There's a hardware uh, DMA engine for the for pixel handling, so color mode translation, and it has a built-in LCD driver and so on. So it's perhaps made for your washing machine or something, or a fridge, to have like a nice display on your fridge and that kind of thing. Um, yeah, it is a microcontroller. You're right. I yeah, yeah. Usually SoCs refer to bigger chips, like if you want to run embedded Linux and stuff like that. But I guess the definition of SoC is literally system on a chip. So I guess a lot of things could be counted as SoC, but yeah, doesn't matter. But yes, it's definitely a beefy microcontroller. That's for sure. Um, and yeah, from a systems level, like what do we have on the PCB? Yeah, maybe I can show that. I think I have it here. Yeah. So here's an overview. Oh wow, this has gotten some progress. So you can check out this GitHub to get a nice overview of the PCB and schematic. So Jake has been busy, I see. So here's a completely, actually at this point, 100% retrace of the PCB. So all of the traces have been figured out and annotated. And actually, at this point, maybe we haven't let Jake know, but we have figured out what the IC is here, the audio codec. Um, so that's kind of interesting. So at this point, I think we have maybe. I'm thinking if there is any chip that is unknown at this point. I think the LDO was, or DC-DC regulator was also figured out. Um, but yeah, so we are basically very close to 100%, if not at 100%. And here is actually, wow, this is amazing. Wow. So Jake has annotated all of the traces. I don't know how much is left. There are some to-dos here, it seems. But this is this is amazing. Wow. Okay. I am I'm really impressed. Huh. Oh, this is cool. Hmm. Yeah, so there you have it. So this is the PCB. So our STM32 and the external flash. But that's sort of the main things that we're focusing on. And yeah, I tried to get the RTC running with the external clock, but I was not able to. So if anyone wants to give that a shot, please do. I was not able to. I configured it and I got stuck in the init function, basically waiting for the oscillator to do anything, but it timed out all of the time. So I don't know. There's something I did something wrong, and I couldn't figure out what it was. Okay, so wow, let's get back to the code. Um, so I guess right. Yeah, I guess maybe this will be a bit boring to watch, but I think it is worth spending some time to Just gonna push the red zone. Yeah, to sort of re-implement this sort of structure, because our structure is kind of hacky. I should get build this. Really nice progress. Yes, I'm really impressed actually. This is next level. Wow. Okay. Okay, we can prefix the RetroGo stuff with the RG. That will perhaps make it less confusing. And then we need to adapt this a little bit so we can build it. So I'm gonna stub this out just to make it build. So first of all, we don't really need to do this. Or we can call this anyway. Okay, so retro loop. This is sort of the main loop. It is in the same file. Okay, that's good. So let's move this up a little bit. X-rays helped a lot. Yeah, definitely. So in case you didn't see that, we can take a quick detour to Twitter. There we go. And I think it was this one as well. Yeah. So Daniel Cuthbert made some nice X-rays with this fancy machine, where we got some. These are the bonding wires inside of the STM32. And these round things are vias, and this is one SMD pad. And yeah, that was pretty nice. And Daniel Padilla also gave us some X-rays. Very nice. And we also had access to the full raw shots as well, so that really helped. But yeah, this is this is really amazing. It's nice to see people helping out like this. Really awesome. How many layers? Yeah, so I think it's 4, but it seems that only 3 are being used, or I don't know honestly. But we definitely have a ground layer and probably a power layer. But yeah, I haven't really looked at it in detail. And if you look at the X-rays, it's actually not that easy to tell, because here it only looks like we have the gray, the darker gray, and the even darker gray. So it looks like it's only 3 layers. But who makes 3-layer PCBs these days? That seems really odd. Yeah, it's probably 4 layers, but on the X-rays it almost looks like there are only 4 or 3 layers, like 1, 2, and 3. Yeah, I don't know, but 4 layers seems most likely. Okay. Yeah, okay. I mean, usually you use the second layer as a ground layer and then the third layer as a power layer. So I guess they have done something similar. Because usually you want ground to be on top below the signal layer so that you get good impedance, or at least not horrible impedance. It's always good to have a good return path for your signals. Mm. Not sure what this code is doing. Seems to do something with the version string. Yes, I haven't implemented any persistent settings. That will be... yeah, this is a lot of work. Okay, so this code is full of callback functions. Okay. So I guess this is the settings menu. Just gonna stub out this a little bit. I just want to get to a sort of a good initial state. So solid ground is not always a good return path, especially at high frequency. Hello. Yeah, signal integrity is something that I really want to learn, especially with really high frequencies. So I have a couple of PCI Express PCBs that I'm sort of working on, and yeah, when you're at basically over a gigahertz, yeah, it gets interesting. And the more you read about how signal integrity and return paths and so on, how that works at higher frequencies, it basically becomes magic. It's like RF, or it is literally RF. Yeah, welcome to the stream. Okay, so we still have some issues. We need to build this file, of course. So let's do that. Now we should get the linker issue. No? Oh, right. I need to... this is a little bit annoying. Should add this one. So every time... Oh. So every time I change the makefile, it will issue a rebuild. Now we should get the conflict. Yeah, exactly. Thank you. But this is a little bit too much. Is there going to be a video explaining the exploit used to reading out the firmware? One of the videos showed his code being loaded into the external memory of the unit to read out the firmware into RAM, but I'd like to know why that was able to work. Yeah, I think Stack Smashing might be working on something, or yeah, I think he is, but I don't want to promise anything in his what he's doing. But I can explain a little bit quickly how it works because I have the code here. So I did some explanation on a previous stream, but I can do a quick recap because it's a little bit interesting. So what we're doing is, so in case you don't know, there is this backup project. Where do we have it? Here. So you can go here to back up your own device. And all of your all the answers to your questions are in that repository. So I can just help out to point out what we're doing. So the scripts go from 1 to 5. We start with a sanity check that we have all the tools installed. Then we do a backup of the external flash. So what this does is that we have prepared some firmware that dumps the encrypted external flash into RAM. So this is no exploit, just the pure code. Yeah, let me just backtrack a little bit. So the STM32 microcontroller on the device, when you buy it from the store, it is locked in the RDP level 1, which allows us to execute code in RAM, but we cannot read the internal flash. So what we do is that we upload, we use OpenOCD here to upload flash dumper, which initializes the external flash and copies that into RAM. So it copies the encrypted external flash into RAM. So this is basically, instead of having the user to put clip-on wires onto the external flash. So this is like equivalent to having an external flash reader. So we execute the code from RAM, and then we wait for the copying to finish, and then we just dump the RAM into a file. So now this flash backup.bin contains your external encrypted flash. And then we do a checksum. Yeah, we copy a part of it and we perform a checksum of it. And we, or not checksum, but a hash. We hash it. But we also copy the ITCM. So that is part of the internal RAM. That is then used in the next stages. So in the third stage, we back up the internal flash. And how that works is we found, okay, so there are multiple things going on here. So first of all, the external flash contains encrypted code that is being decrypted and placed in RAM and then executed. And the method of the encryption is explained in a different video from stack smashing. But it's basically XORing, I mean, it's AES in counter mode, which means that if we know the plaintext, we can forge a different ciphertext. So we prepare some payload, which is this assembly file. So it's a nopsled plus a memcopy function, where we copy from the internal flash to the RAM that we can then dump. So we then encrypt this payload using the internal RAM backup. So using the backup of the RAM and the external flash, we get an XOR key. We use the payload and encrypt that with this key and put it in a new binary. This is then being written to the external flash using Flashloader. So at this point, we have a binary which contains the external flash, including our encrypted payload. So after this stage is done, the device now has our payload in the external flash. Then we ask the user to power cycle. And then what happens is that our payload is executed and it will copy the internal flash to the RAM, and then it will crash and end up in a hard fault handler, which is just a while loop. So we attach the debugger and dump the RAM into a file. And now we have the internal flash. That is how it works. And then step 4, it changes the RDP level from 1 to 0, which causes the internal flash to be wiped by the device itself. And then finally, we restore the internal flash and external flash with the backups. And now you have an unlocked device that is running the stock firmware but is debuggable. So that's how it works. And I'm sorry for the bad explanation, but yeah, this is not the cut video. Yeah, you're right. But I don't expect people to go back and watch all of the streams. It's a lot of hours. Is the key the same for all devices? And this code means that you don't need to put the key into GitHub. Exactly. So the funny thing is that the bulk of the flash is the same. But actually this method doesn't require any key at all. We because of the method that stacksmashing has explained, because it's using AES in counter mode, we always get the same. Like we can forge the external flash without knowing the key, because if we know the plain text and we know the ciphertext, we get an XOR key that we can use to forge our own ciphertext. And yeah, stacksmashing did an amazing job at explaining this. It's very, very clear. So go check out this video. But what I just explained is exactly how the exploit works. So I mean, it's a very simple exploit per se. It's not really an exploit. It's just a method. So we have this NOP sled, which is a way to allow us to execute from anywhere. So basically, this is just in order to ensure that the loader code that is in the internal flash, it will execute code that is loaded from the external flash, but it might start at this position or this position. I don't know exactly where it starts, and I don't really care. So by just having an sled, we don't need to care. And then here is just a mem copy, basically, implemented in assembly. And that's basically it. So the whole magic is that we figured out that there is code stored on the external flash and that we are able to forge it. So yeah, that's it. So now you know how that works. Let me just yeah, and actually your question is still valid, Codebauer. Is the key same for all devices? The truth is that yes, it is, for some reason. It didn't have to be, but it is. Is the loader code in all ROM? You need the extra pattern for Homebrew. No, no. So for Homebrew, we overwrite the internal flash as well. So for Homebrew, we expect people to back up and unlock their device. And now we fully own the device and put stuff wherever we want. We don't have to care about anything. We don't have to make it compatible with the stock firmware. This is 100% homebrew, which also makes it easier for like copyright reasons and so on. We don't need to publish patches to the original firmware and so on. This is 100% own code. So, which is very nice. We don't need to care about anything. The only sort of trace of the original the only trace of the original firmware is the hash, basically. But that is it's just a hash. It's a fingerprint. It doesn't tell you anything about the content, so this should be fine. So the way the script works is that we verify that the backup was successful. Hi, Tixley Geek. Yes, I was just explaining how the dumping works. Okay, so I guess we can go back and do some more coding. So, where were we? Right. Yeah, so let's do an emulators init. So now I need an extra file called emulators. So let's copy that. Let's just prefix it. So this is probably gonna not build at all. Yeah. So we need a few more files. Yeah, of course. Now we get some specific errors related to the ESP32. Let's look at those. So what does add emulator actually do? this is some ESP32 or ESP SDK specific code. So I guess it's using this to sort of reboot into a different boot mode, like a different reset handler. Like it sets up some external flash pointer and then reboots, I guess. But we don't really have that luxury, so we cannot do that. So let's just set the placeholder. Okay. Now we just have some linking errors. Not just one or two. Let's clean this up a little bit. Okay, where do we set that? Did anyone try the Pico 8 emulator? The video demo looked slow, but maybe just the game. Codebar, could you please link to the Pico 8 emulator? Because I've been trying to find a Pico 8 emulator and I am not able to find one that is actually portable to a microcontroller. I think I found some Lua project that was looking promising, but I am not sure if it was actually, fast enough or small enough and fast enough for a microcontroller. I think the most promising I found was for the Raspberry Pi, which is way, way beefier than this. So please, if you have any links to share, please do. I've been trying to find some stuff, but I haven't found anything. Yeah, let's just stub this out. Just gonna comment this out. And obviously we're gonna implement this someday. Just not right now. So actually, I don't really know what the return value is supposed to be. Yeah, I don't know. Nice. Yeah, this is gonna be really nice once we have this in place, because we're actually able to switch between different filterings and so on. Yeah, this is gonna be really nice, but we don't have this right now. Okay. What does this do? Speed up. Okay. Let's not do that either. So there's still tons of undefines. Kind of annoying. Just gonna go from top. So maybe we need to implement this actually. Yeah. So I'm just gonna stub this out. Yeah, right. This is what I also found, the ELUA project. This seems promising. But I still think we need some 2D accelerator code, I believe. I haven't looked in detail, but like the whole pixel blending and pixel, you know, the whole 2D layer stuff. I guess we need to do something about that. Oh, it seems I broke the build. So the good thing with the continuous integration is that you actually can see when you break stuff. So it seems my last change actually broke something. Well, it is how it is. We can fix that later. Yeah, so what were we doing? Settings. Yes. It's a start. This needs sound synth and a lot of Pico 8 specific stuff. Yeah, definitely. Okay, I need to build the MZ, this one as well. Okay. Okay, this looks funny. Pico 8 is really limited to game developers, like screen size, memory size, etc. But on hardware, it's a Lua and no limits on Lua code resources. Okay, I actually have zero clue about Pico 8. I I've just seen cool stuff being done in it. Lua uses hash tables in dynamic memory allocation. Yeah, that's true. but that doesn't have to be a problem. Like we have quite a lot of RAM, like a full megabyte, um, and if we can find a good fast memory allocator, I guess we can yeah, we can do some cool stuff. But I guess it's quite string heavy with the key names and so on. Um, so maybe it eats a bit of memory and so on. Yeah, I'm curious about how this is implemented. Yeah. So this actually doing like a full reboot of the system. That's interesting. I mean, we could do something similar, but I'm not gonna focus on that right now. We just want uh, something running. So I guess we just need to stub this out. Um, yeah, this is a huge to-do. Oh, there's another. Luamin, a minifier. Ah, okay. Yeah, that might be useful to make the code smaller. Why? Okay, we're gonna need to do something about this. So, what are we actually doing here? Okay, so here it's actually initializing the. Okay, so it's. Let's just hardcode this for now. Uh, ah. You obviously need to do something smarter, but let's just put some stubs here for now. Why don't I have assert? That's weird. I have broken something. Yeah. See you later, nickname. So what I'm looking at right now is that for some reason the external flash is 0 bytes. Maybe it's because the compiler has pruned so much. Yeah, probably. That's probably why. Okay. It looks different. There is sort of a blue shade. It's a different flavor of broken. And it isn't crashed, actually. Okay, the buttons don't do much. Oh, look at this. It actually does something. Okay. Well, this is interesting. It's a first step. We have some crap on the screen. Let me just move this a little bit. So yeah, there you have it. It's basically done, right? It's just some tiny tweaks left. Yeah. So I think first of all, we need to think a little bit. We yeah, we are in 565 mode. So I'm just thinking if there is something broken regarding that. Okay, but I'm gonna. I don't know. I guess we just need to figure this out. All right, I should adjust this as well. There we go. So I guess what we can do is to just, does it have a font specified? Oh yeah, good point. It's probably, I mean, I've stubbed out so much, so maybe it's, that's why it's broken. I mean, it's quite likely. Because I stubbed out all of the settings. Where do we have that? Oh, it's all the way down here. Yeah, so it's probably using these functions, which are just stubbed out. So the question is, how do we do this in a good way? Yeah, so what I'm thinking is happening. Actually, we can debug it. It's probably doing this, some sort of setting get. Oh, sorry, let me switch screen. And sorry for the wobbly camera again, sorry. Break one. Okay, so here we can actually check what it's requesting. So cell.nes. No, okay, I was wrong. Because here you have the font size.get, and I thought maybe it's being used. Yeah, okay, it's not even being called. Okay, we can debug this in a more logic way. Let's go back to the main loop, rg main. So this is our entry point. again, here's the entry point. We do emulators in it, which adds stuff to the tabs and so on. Yeah, exactly. So first of all, maybe we should double check that this actually works. So GUI tab add. So here you have the GUI struct. So it has 2 tabs. Tab count is 2. That is good. Let's print the first GUI tab. Let's just move it up a little bit. Maybe I should just do like this. So here we can see that we have the first tab is the NES tab, and we have faked that we have one game. There is a reference to the logo and the image. Yeah. Emulators. So that seems fine, I guess. Oh. Okay, so let's go through the rendering code then. Where was that? RGMain, retro loop. Yeah. So this one does quite a lot actually. Yeah, I mean, it's pretty clear that something is wrong with the rendering, but it could be the whole memcopy thing that's not correct. So draw header, what does that actually do? It has some fixed sizes. Odroid display right. So in the top left corner, this will write stuff actually. Oh, the fill rect. Is that implemented? It is actually. Oh, this is not. Oh, no, it's using dynamic memory allocation. Yeah, I need to get rid of that. So just 1 second. Okay, no big difference, but we still have some allocation. Okay, wait, I'm gonna break malloc. Then we can find who's allocating memory. Okay, it seems nobody is actually doing that, so. Maybe I should start with something simple and just verify that the drawing works, which means that I need to understand how this works. So instead of doing this, let us do our own while loop and render our own things. So instead of calling GUI redraw, we're gonna do this manually. So let's see if we can do any of this. Yeah. So we want to do a rectangle. We want the whole screen to be, let's first make it black, and then let's make a white square in the top left corner. See if that works. Okay, this definitely looks broken. So first of all, I think we have a bunch of problems. Where was this implemented? I can't remember. Oh, there we go. So, yeah. Right, the active frame buffer. So, who sets the active frame buffer? But this code is probably not... I'm curious. I need to debug this. That's not even implemented. Okay. Kind of confused here. What are Odroid screen costs? Yeah, good question. I wonder if these are valid, like if these are actually being used. Yeah. Oh god. Yeah. So this proves that we're actually including this file, and we have 320 by 240, which is correct. So again, we're getting this sort of blinking pattern. So it seems that it's writing only half of the screen. It's not like a DMA issue. And yeah, it actually looks like this in real time. Like it's not a camera issue. These bars are, yeah, that's how it actually looks in real life. So if I change color here to something else, let's say blue. Okay, so I mean we are able to, we almost have control. We just don't quite understand what's going on. Yeah, and the pattern you see is just the camera that can't really display this in a good way. So let's cap the frame rate and see what happens. Oh, look at that. It looks better. Still bad. And the reason for that is because we are not, let's see here, main GB. We should actually yeah, we should have this code. But yeah, I really don't want to do this. Oh, this is gonna take like forever. But to keep things simple, maybe we can live with. I don't know. Yeah, because this code is probably being executed. Yeah, I guess. No, let's not do this. Let's just focus on getting something decent on the screen instead. Because otherwise we're gonna be here until midnight. Yeah, so this looks quite bad, but don't mind that. Don't mind that it blinks a little bit. We can fix that later. But this means that the drawing function actually works. The screen offset is correct, the color is correct, because if we do red, for example, it will be red, right? Yeah. So this, and also the size works, which means that our width and height is correct, and our blit method is correct. So at this point, I'm confident in that we can write pixels correctly. So now the question is, why can't we draw text correctly? What is wrong with that? So let's just take some code that draws some text. Yeah, so first of all, there's this. So this way we can check what the font size evaluates to. And then somewhere we should draw some text. There we draw some text. Okay, we can copy that code. So let's draw that text here. Let's draw it 100 pixels in and 100 pixels. And let's check the arguments. Width, okay. I'm not sure what width means. It is pixels, okay. Yeah, we have looked at this code before, I remember it. Here it's actually hard coded to the 8x8. Okay. Yeah, let's do like this. And it takes a buffer. Okay. So hello world. And then a foreground color and a background color. Okay. So let's write blue text on green background. Cool. Let's see if it works. Okay, it looks horrible. It looks really, really horrible. And something is clearly wrong. There are multiple things that are wrong here, actually. So first of all, I thought that we have an X position here, but our image is in the left corner, like it's starting at offset 0. So something is clearly wrong here. Let us step. So why does it disappear? Oh yeah, it disappears because I have a breakpoint in here. Okay, never mind. Okay, let's check it out. What are we doing? Yeah. Where am I? I am here. So this is our copy of the Odroid overlay C file. And the reason why I copied it is because I thought I needed to make a bunch of changes to it. And maybe I do. So just gonna look at the original code here for a second. Yeah, okay, so I've already destroyed this file a little bit. Oh yeah, it was the overlay buffer, right? But that should be fine. So the overlay buffer, it gives us basically 64. This is quite huge, actually. Yeah. 40 kilobytes of just like a scratch buffer. That's that's a way to waste RAM for sure. I'm actually curious about the allocations. So the DTC RAM, 52 kilobytes, yeah. And if we sort of make this into 1, what do we get? Okay, okay. So the DTC RAM is basically all used for the overlay buffer. But yeah, we can optimize this later. No need to focus on that right now. So yeah, let's debug this a little bit. So just gonna move this window a little bit. So So here it is preparing the overlay buffer. Oh, maybe I forgot something when implementing this memcopy thing. Yes, now I see it. Okay. Yeah, I have to change a little bit here. So the issue is that I'm not using the left at all, so we should add that to here. Okay, it looks better. Still weird. Something is still wrong. It doesn't say hello world at all. So let's figure that out. But at least the offset is correct now. So that's a step in the right direction. Font lib. Yeah, it's using glyphs, like, you know, so each character is 8 bytes. And I believe this is a binary, like it's only 1 and 0. I haven't checked, but I believe that is the case. Because then you get 8 by 8. Yeah, exactly. So each character is 8 bytes times 8 bits. So 8 by 8. But yeah, as you can see here, something is broken, really broken. So I'm trying to figure out what's going on. So we have this draw text line function. So something is not working out here for some reason. So let's try to figure out what. So now we are at line 23. Maybe try with one character. Yeah, thanks. That's not a bad idea. I'm gonna use this like inner function instead. And why is my editor not happy? Oh, maybe this is an internal function. No, should be exported. No, it's not in the header file. Okay, so let me just do that. Font pixel format doesn't match the one used for frame buffer. Yeah, so the font is stored in a single bit, 1 bit per active pixel. At least that's what I gather from looking at the font, wherever that was. Yeah, so this looks like it's 8 by 8. It's called 8 by 8, and it's 1, 2, 3, 4, 5, 6, 7, 8 bytes. So I believe this is a 1 bit per active pixel. And then here we are sort of preparing the scratch buffer and the overlay buffer with the glyph. So let's try to, we can read this code and see if we can find some issue. So we're stepping the number of characters in width. So for example, if you have let's say you have 8 characters and the font width is 8 bytes wide, or 8 pixels wide, sorry. Yeah, then we get one iteration here, which makes sense. So maybe we should think about that. So where is my main? Okay. So exposition. Yeah, let's make it simple. Let's do it at offset 32, y position 32, with. Then we take 8 times 8, And then the text can be 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And the color, yeah, let's just copy that from here. And let's try it again. Okay, so I'm showing you the frame buffer. So it looks like the offsets seem to work. The 32 pixels from top and 32 pixels from the left. And the length seems to be correct as well. But yeah, if we change this to just one character, so now I'm just typing a capital A, and that doesn't work at all. Okay, so let's understand why. Okay, so let me switch. Okay, yeah, so let's break on. Yeah, where the hell did that come from? Okay. Okay, this is actually, it looks quite efficient. Oh, but this is, what? This is never gonna work. No. Okay, I think I need to just think for a while. So we go to the offset, right? Stupid idea. What do you mean? Maybe if you need to draw a pixel. Well, so what we're doing here is we're bit masking out 1 bit per, we're basically iterating through the, maybe you need to use the or equals. Yeah. No, so what we're doing here is that we are, I mean, we could, so we're setting it to either the foreground color, or the background color. And the overlay buffer, what is the data type? It's should be pixel t, but it doesn't really matter because it should be in 16. Offset. Yeah, don't worry about it. I get it. But yeah, you could do some blending here. Like this could actually do alpha blending if we wanted to. because our frame buffer is... No, actually, this will not do it. We would have to do it in this one. Well, never mind. So let's see if this actually is correct. So again, we're trying to print a capital A, and our glyph... Wait, this is not right. Or is it? Okay, it's actually a two-dimensional array. Okay, I get it. So first we get right. So this glyph has 8 entries, right? So let's just verify that it found the correct glyph. So this is the one. So this actually seems correct. Yeah. That matches, right? So that's cool. Is something wrong with this then? Scale is 1. That's good. That is 8. That is also correct. So, wait. This doesn't make sense. This never increments on the y-axis. Shouldn't this be like so? What? Oh. Yeah. Okay, this still looks like crap, but so my thinking is that I don't understand what's going on here. We have a glyph, which is a pointer to the active glyph, and we have verified that it is the correct one. With other words, we have verified that glyph is indeed pointing to this entry. We know that. But then this actual code, it should scan the glyph from top to bottom, right? Oh, right, we have y divided by scale. Okay, never mind. I was ahead of myself. Get font width. Yeah, good point. Good point. Okay, it seems it's not even being called. I mean, I'm returning 8. Okay, maybe it's being automatically... yeah. Same goes for height. Yeah, and I think... Didn't we verify that? So here I'm stepping through the for loop. So just going a few steps. Oh, holy shit. What happened here? I think something is wrong. What? This doesn't make any sense. What the heck? What? I don't understand what's going on here. We have X and Y. Why? What? Let's do this again. Okay. We have I, and then we have it skips sort of over the line 71. That's this one. 73 is this one. 77 is this one. So anyway, I guess it's getting inlined, so we don't really see it. So let's do, how do you do this again? Is it like this or like this? There we go. Now we can actually debug this. Okay, here we go. Okay. I don't understand why Y is this broken. Oh. Oh. What? But didn't we check this? That this actually returned 8? It is 8. What? This does not make sense. Okay, so this function, it returns font size, which is 8. I honestly don't understand what's going on here. Okay, it's still broken. But I'm gonna hardcode these because I don't get it. Okay, it's still broken. But is something wrong with this code? Because it doesn't look that... Let's hardcode this to 1 as well. Okay, let's just think a little bit. So again, this is basically for each character. And here we get the glyph for the active character. And then we scan for each line and the font and the glyph. So this one should iterate from 0 to 7. and then we have an offset where we take the current X offset in the destination buffer and we add the width times Y. So this is to get the offset in the destination buffer. Yeah, that's what we do here. And then we do plus X, which is correct. And we take the active glyph at the current Y position. Yeah. And we mask out, how could it be this? No, okay, still looks good. Or still looks broken. We take a 1 and we shift that left with the current X value, which makes sense. And if it's true, we do the color, otherwise the background. And then what happens later? We do this 8 times. So we increase the overlay buffer. Is the overlay buffer, it's UN16, which is correct. And the colors are also 16, right? Yep. And I really don't see the issue here. I don't see the problem. I'm gonna add a print. Let's split this up a little bit. Okay. One question. I see your programming time is too fast. Are you using external Flash? No, so actually programming the internal Flash is really fast. It takes less than a second. And the Flash is only 128 kilobytes. So it really is this fast. Just to illustrate this, I can go to the main function and change the background color like this. Boop. So you see, it is really this fast. Yeah, you're right. I can do that. But oh. But yeah. Okay, I'm gonna increase the log buffer. Let's make it 16K instead. And then let's put this in a different editor. All right, it's enough with just one full. Okay, so what do we have here? Yeah, I could have added a new line, but yeah, let's hop to the font. So this is what we're looking at, right? So the first row, let's verify that. Okay, 0, 0, 1, 1, and then 0, 0, 0. So that is correct. Yeah. So I don't. So what could be the issue then? Is this wrong? Our overlay buffer, is that being copied incorrectly, perhaps? We can actually dump this. So I'm gonna try something now. Mon dump image, call it font.bin, and then I need the address of this one, right? Yeah, there we go. And then I'm just gonna open this in GIMP. So just 1 second. So let's think a little bit here. What is the width of the overlay buffer? Is it this one? Yeah, I guess so. Which should be 8. Ah, look at that. It's an A. This is GIMP. Let's do like this. Check it out. So we are actually getting this. So something is getting messed up later on. So now we know that. That's good. Now we have some facts. So nothing is wrong here. This is correct. Then this is the issue, I guess. Because what we did just now was to dump the actual memory of the overlay buffer. So let's break there. So our argument is left 32 and top 32, and that makes sense because we want to write at that offset, which is fine. So let's continue. Height is 8, that is also correct. We have verified that both the width and height is 8 of the actual buffer. Right? So is something wrong here then? In the destination row, the destination row is where we want to write to, correct? And we don't know anything about that here. We only know the X and Y position. We know the width of the buffer and the height of the buffer and the pointer to the source buffer, correct? All right, see you. And here we get a yeah, so this is the destination buffer's size, the actual frame buffer. So we want to copy. Oh, now I see it. Now I see it. Oh, here's the issue. Oh shit, that doesn't look good. Okay, let's think here for a while. Right, it's the wrong data type. So let's write it nicely instead, and do like this instead. Yeah, that should do it. It still looks broken. Why? Okay, so just to explain what we're doing here, we want to copy from a buffer that has the dimensions width and height. And stride. Oh, of course. We should use a stride. But the question is, which unit is stride? It's in pixels. Okay. So it should be the same. Okay. So we want to copy one row at a time. So from buffer, we go to the current row. No, okay. Now I see. This won't do. We need to do like this instead, and do like this instead. Yeah. Yeah, here we go, finally. Yay, we can write text. This took longer than it should have, but at least now we know what's going on. We understand the glyph code a little bit better. So it's not a complete loss. So yeah, let's go back here and see if this works. Yay, we can write hello world, and it looks like shit, but in reality it looks okay. Maybe if I turn it a little bit. Yeah, it doesn't look as bad as on the stream, actually. Yeah, okay, so there you have it. Now we can draw some text. So now we can remove this and do like this. And, oh, check it out. Check it out. This is exciting. Thanks, JTH. But we can do it better. We can make it look nice if we want to. Now we understand the code and we can improve it. So it doesn't show that good on the LCD, but there's a blue gradient, which looks pretty good, actually. No, it doesn't. There should be dithering or dithering. But yeah, don't be too excited yet. Nothing works, but it's a step. Oh, check it out. Ooh. Right, the buttons don't work. There's a lot of work left to be done, but yeah, it's a good first step, I guess. I guess I should put this on a branch so I don't mess up too much. But yeah, I think this is a good place to end the stream because yeah, we've done some stuff and I need to clean up, and that's really boring to watch. So anyway, here you have it. We can draw stuff finally. And in the end, I guess, yeah, the biggest problem is probably the settings. We need to find a way to store settings, and then the whole SD card integration, because we don't have a proper file system. We yeah, we need to find a way around that. So I honestly don't know really which direction I want to take on the whole SD card thing. Like we could like compile a file system. Like we could come up with our own tiny file system with like static entries that you can sort of compile time build, that you build your tiny file system during build time. Like for example, let's say you put your ROMs in a directory, and then we have a script that will iterate and build a C structure based on that, and that's it. So I think that could be a way forward. So anyway, thanks for joining, and I think what we have now is, let me just show the whole screen. 1 second. Yeah, so that's how it looks. So anyway, thanks for joining, and I will be stopping the stream now. So see you next time.